As we're coming to a close, we have about an hour. We have extended this to 5:45. Originally it was 5:30. We have an additional 50 minutes if you so like, which is great, because we're very fortunate, Nino and I, to have such a great panel of speakers. But rather than introducing every single panelist, you'll learn a little bit more about their backgrounds as we go through this panel and have this conversation. If you want to read their bios, it's available on the website. But just a very, very quick mention here. So we have Rob Almgren, who is on Zoom here. We have Mathieu Dixon, also who's online, and we have Lisa Huang. All three of them are in the on the east coast of the U.S., more or less spread out a little bit. We have Fabrizio Lillo, who's sitting here, who you met before, Mathieu Rosenbaum, of course, and Nicholas Westray. And we also are fortunate to have Thomas Wolf with us from Hugging Face here as well. So thank you all for being here with us. Nino and I will be moderating the panel. The format we're going to be following here is we have a number of questions prepared that we thought that we'd go through, and then towards the end we'll open it up for general discussion and questions from the audience, if you so allow us to. So what I want to start off with is to turn to Mathieu. I think you can hear me back there. I want to ask the first question to you, and the question is, what do you see as the most important trends and new developments in financial decision making and time series analysis today?
So first of all, thanks for the invitation, and good evening to everybody. Good afternoon to others. Good morning. And let me first touch on a few of the main sort of problems and a couple of the sort of, I think, most important open problems. I think in finance, as opposed to other areas, I think we've learned that one of the challenges is the low signal to noise ratio in time series data. We have the problem of non-stationarity. Data is often, or markets are often very event driven. You also have issues of conditional heteroscedasticity, which is a problem when you're trying to sort of model things like volatility. And quite often there is a high degree of correlation across instruments in the market. Combined with that, I would say that what we've learned in sort of over the last 6-7 years collectively as a community, and some may beg to differ on this, is that quite often just having the increased representational power of deep learning isn't enough. And this is partly to do with the low signal to noise ratio. And so you could be essentially very easily overfitting. Now, I think that the main open problems here are around, and I've tried to sort of be mindful of the speakers this morning, which I couldn't unfortunately join to listen to. But I think the main sort of, if I could summarize here, I think overall in the industry, I think you've got the problem of model-based machine learning versus let's call it data augmentation. So this is one area. And let me just say a little bit about that. That is essentially the challenge of how do you combine models that potentially represent well-known stylized facts into machine learning. It could be PDE-based models, for example. We did this with Stefan Kreppe in local volatility modeling. It could be combining other models for stratified sampling and in trying to regularize in a better way. I refer to the work of Marcus Pelger, for example, where he combines no arbitrage into asset pricing to create a deep learning-based approach, which has these other constraints embedded into the models. On the other hand, you have the other school of thinking, which is it should all be about data. It should be data augmentation, should be using GANs to generate more data, and then fitting your regular classical off-the-shelf model to it. And I think these two are trying to overcome the same problem, which is the overfitting problem. But I think the advantage of model-based machine learning is that you actually solve the interpretability issue, at least partially. And that brings me to the second topic, which is, how do you integrate more advanced statistical know-how methodology into computer science algorithms? How do you integrate frequent statistical testing in a meaningful way so that you can do model selection based on principal hypothesis testing. You could do rigorous statistical interpretability. You can use Mariano-Diebold tests to say whether one model is different from another. So I think we are still in this stage of not having enough rigor in sort of deep learning and other areas of machine learning. And I would extend that to experimental design, optimal sampling of data, and even Bayesian modeling, and how to do that in a very effective way. And so these are, let's say, the main sort of topics that I think are open. Of course, I'm missing some other areas, but these are, from my perspective, what are important. Thank you.
Thank you. So in the next question, it can go along the similar lines. So today, Mathieu Rosenbaum, you have been speaking about actually also a bit about the model-based methods. In particular, you were showing some partial differential equations. So can you give us your view also, like what are the, we know what are also some pros, but can you also tell us what do you see as pro and cons when you're using model-based and with respect to just data-driven, so to continuing in the similar discussion?
Yes, I kind of agree with what was just said. I really think that the use of machine learning and so on in finance, it's kind of fascinating. And everybody's doing that, right? So I'm heading a master program and 90% of the internship of the student, it's about machine learning in finance. Like it's so trendy that everybody has to try that. And I think now it's part of the toolbox of every reasonable quant. That said, I mean, it's machine learning, and learning is hard in finance, right? Because it was said during the talks, I mean, finance, I mean, there's not too much stationarity in finance. We believe we have a lot of data, but maybe in fact we don't have so many data. And I mean, there is kind of a no arbitrage principle which is out there, which means that learning, forecasting is complicated in finance. And I think that the future of machine learning in finance is not only about prediction. I mean, to do just prediction in machine learning, I mean, in finance, which was the goal of machine learning, I mean, initially, I mean, you have to be like super strong to improve what already exists. You have to be as strong as Nick, I mean, to do something to forecast, I mean, to gain like 1%, 2%, it's super hard. On the other hand, I mean, 2% can be already a lot, I mean, like in your case, I guess. And on the other hand, I think it's fascinating to see how this machine learning technique, they can help you solve problem you could not even dream to solve before. I mean, for example, with Thibaut Gesson and other people, we've developed these rough volatility models. And 10 years ago, it would have been just impossible to calibrate them. And using this mathematical modeling framework plus the machine learning techniques, now we are able to calibrate them in like 1 second. So we can do that. I mean, you can solve optimal control problem with PDEs that you cannot, I mean, that are super complicated, and you can do it in an efficient way. So I really think that part of the future of machine learning in finance is to be combined with a mathematical approach, and in particular in the cases where you can do some Monte Carlo. Because as you said, we are limited with the number of data, but as soon as you can do Monte Carlo, well, you can run your Monte Carlo for like maybe 10 days, and then you can do your machine learning on that. So if you have like infinite number of data, like when you can do Monte Carlo, I think it's a very relevant approach. Although I'm not claiming that you cannot forecast anything, but forecasting is very hard in finance in general. And the last thing, I mean, I'm hearing a lot the hedge fund manager and so claiming that everybody is making tons of money because everybody has great machine learning techniques. Well, it's hard to disentangle. I mean, are you making money because your machine learning algorithm is better than the other? Or are you just making money because everybody is making money this year? It's hard to disentangle.
Great, thank you very much for that, Mathieu. I'm going to turn to Rob Almgren, who's on Zoom here with us today. You're in a unique seat as a chief scientist at Quantitative Brokers, and you've been a market practitioner and also an academic for many, many years. So maybe from your perspective, can you share with us where you have seen AI and machine learning in finance being effective, and maybe talk a little bit about how you are thinking about it?
Sure. Thanks very much. I'm really sorry I can't be there. And also, speaking of academics, I have to respect the original end time because I actually have to teach about signal generation in finance at 11:30. So speaking of what we do at Quantitative Brokers, we've had success in two areas. One the biggest single area where we've had success with machine learning is in cost modeling. So we do agency algorithmic execution in futures, and futures have the problem that they're much more heterogeneous than stocks. You can't just scale by, by daily volume and volatility and use a model from one product for other products. It's not like stocks where they're all kind of the same. We have futures on a dozen different exchanges around the world, and they're interest rate futures, equity index futures, commodities, and so on. And so we all the time, our clients want to know, if I execute a trade of such and such size, what's the expected slippage? And for products for which we have a lot of historical trades, we can just calibrate a regression model and give a very good estimate. But we have a lot of demand for cost models applied to products that we have very little data for, and even in fact products that we haven't traded at all. When we opened the Japanese exchange a few months ago, clients were saying, well, what's your predicted cost for the Japanese equity indices? And one of our answers was, we have no idea because we've never traded it. But that's not really a good enough answer. So one thing we've been able to do is use a variational autoencoder to encapsulate about 15 different dimensions of market microstructure, that is things like volatility, traded volume, and so on and so forth, to classify different products into different regimes where we can use models from one product on other products. And we've been able to actually then derive cost estimates for products where we have very little data and have even not traded. So that's been a huge success. And another place that we've, somewhat to my surprise, been successfully able to use machine learning, specifically reinforcement learning, is in designing from the ground up some new strategies. So we all the time have the challenge of, we place a limit order in the market, how deep should we place the order, when should we decide to cross? And by using some sort of astute design of how we run the simulations to not take too much computing time, we've been able to calibrate using just a blank slate, a raw neural network reinforcement learning model, calibrate these kind of decisions and come out with really measurable, better results. I should say things that we have not tried to do are what Mathieu just mentioned, and Mathieu a little bit, which is generate random data. I'm not really a big fan of that because, well, I like to look at specifically at the real data, so we've had some successes with that. And then, as always, the problem with machine learning, as Mathieu said, all the students want to do it. Here at Princeton, I get a steady stream of students who say, I know a lot about machine learning, where can I find applications in finance? It's so seductive because you have massive quantities of data, and it seems like you ought to be able to parse that and come up with trading signals. And it's just not so easy as it looks, because it really is almost all noise. If there's any signal at all, you're lucky. So in these two particular, very focused areas, we've been able to have some pretty good success. So that's all I would say about that.
Thank you. Okay. So the next question goes to Fabrizio Lillo. So from your point, you have been also the whole day on a workshop, and you have been seeing a lot of presentations. So with your background in complex systems and econophysics, what do you see as an advantage that, again, it can bring for, let's say, development, not just the machine learning for finance, but also machine learning in general?
Okay, so I think that there are different answers depending on the type of system you're interested in and what is your purpose of what you're doing. Definitely, I agree a lot with what Mathieu and Mathieu, the two Mathieu said about the importance of machine learning in time series analysis, but also the difficulty that you encounter in finance, essentially, as I was trying to explain during my talk, because you have this non-stationary behavior, you have change of regimes, and you have to be fast in adapt your estimation to this change in regime in order to react. This might be sometime at odds with maybe the use of models, which requires a lot of data to be calibrated and recalibrated each time. Another important aspect still for time series, I think, is related to the fact that sometimes you are interested not much in prediction, not only in prediction, but you are interested in estimating latent variables, so variables that you cannot observe. Okay, volatility is one example, correlation is another example, liquidity another example. These are all very important quantities that you need to know, and for which you need to design estimation methods that are able to reveal this latent structure. These I think are big challenges for which machine learning could bring a significant contribution. Also, of course, using all the blending with all the literature that we have in econometrics about solving this kind of problem, which are of course much more model-based, but in a more flexible way. I would say the other aspect, going more into the complex system, let's say, perspective, I think also there is another important aspect in finance which has not been mentioned so far, again, of the use of machine learning and artificial intelligence, which again is not related to forecasting, but it is related to model estimation. Okay, so there are not only hedge funds out there, there are also other players, let's say, for example, regulators or central banks and so on and so forth. They typically want to build very models in order to take policy decision. Okay, these typically are very complicated models. If they are not complicated, it is because they want to estimate, they want to have a model which can be estimated. And these models are important because the outcome of the model will serve to take important policy decision, okay, or regulation decision if you are an exchange or something else. So an increasing stream of literature that I'm following a little bit is exactly this one. So the use of machine learning and artificial intelligence to calibrate, complicate models, complicate agent-based models, for example, okay, or even complicated time series models, where again it's not so important that you want to forecast what the variable will become, but say, okay, if I believe that this is the model and this parameter means something about that I cannot observe, how can I calibrate this model with the data and get this parameter better than I can do with other methods? And there are many examples of this. For example, agent-based models are a class of models which are start to become more and more used, but are very, very difficult to calibrate because they are strongly nonlinear. There are a lot of nonlinear effect, feedback, and so on and so forth. And so there is a stream of literature which is trying to use machine learning and artificial intelligence to calibrate this model and extract parameters that then can be used by policymakers to take decisions. So this is something where I see a lot of space and a lot of possibility of combining, let's say, these two streams. And I think this could be a very fruitful avenue, let's say, for the future.
Thank you for that, Fabrizio. I'm going to turn to you, Thomas. Thomas Wolf. So you're perhaps the only non-finance person here, and we thought you being here, it's a great opportunity to meet and discuss these matters a little bit. Maybe you can first briefly share what you guys do at Hugging Face, but more specifically talk a little bit about what you see as the major breakthroughs in the area of NLP in the last few years and how that's impacted your work.
Yeah, thanks. I mean, first I want to say I'm very happy to be here. I'm learning a lot. That's really great. So at Hugging Face we are developing, we are building kind of a hub to basically share kind of models and data set and all the things that people use to do this machine learning, basically both the artifacts but also the code. We are kind of on a mission to kind of make AI, democratize what we call responsible AI, which is AI where we try to share knowledge instead of following this kind of a private way of developing models and everyone is competing with each other. We think that if we kind of go together as a community, we can actually catalyze the research in AI and make this both going faster, I would make discovery faster, and also make this in a more responsible way because we involve everyone. So that's what we try to do. This involves working a lot about open source and open science things. We started as an NLP company, and now we're doing kind of more general ML. So we actually just started working on time series 1 month ago, so I'm learning a lot now, still in the beginnings, but I think this is very, very interesting. And to talk more about NLP in particular, I think maybe the most important development is that it just kind of started to work, basically. If you go back 4 years ago, I remember when I hired my first research scientist, Victor. He came obviously from this like master degree in machine learning, and he was really disappointed to work on NLP and not computer vision, because computer vision was really working, and NLP was like this kind of place you go and nothing work, and just nobody's really interested about what's happening in NLP anyway. People were building parsers and things like that. And now the situation is just totally different, right? In a couple of years, like NLP came from this kind of underdog situation to like basically, I would say, the dominant kind of trends in today discussion around machine learning, right? It's first started to work and also now kind of influence all the other fields. So a couple of discovery there. So like the transformers architecture started to be mostly in NLP, now is kind of going all other fields of machine learning, computer vision, reinforcement learning, maybe one day in time series, I don't know yet. It's still kind of tricky, but yeah. So, and transfer learning, which obviously already exists in computer vision, but was kind of very, I would say, narrowly seen, has got this huge boost by becoming the leading ingredient for the explosion in NLP. So that kind of led to a deep question in the fields, also very ethical question, because we just didn't have about, before NLP started to work, people didn't have to worry about what would happen if it worked. So all these questions around ethics of misuse of models that would generate fake news, ethics of bias in the data set, ethical usage of NLP, which are now kind of a big question in the field. Nobody had to ask them before. And now people are like, oh, now what I do has some impact on the world, so I should be very careful. But yeah, so it started to work with the good and the bad sides. And the good and bad sides. Another thing is that NLP has become very interesting medium as kind of both a medium which is some sort of input modality. We talk a lot about what's happening in NLP, right? We're just discovering that we are like a species which talk a lot, and that's kind of a fundamental modality as input. And that's also how we have like sequence and reasoning. And so basically we see like model training NLP now using reinforcement learning, which is like very distant things, but using a model that's pre-trained on text actually help to have a robot that navigates a room. And you're like, wow, why does this happen? And I think this is just the hint that NLP is something very, very fundamental to just human, basically. And so if you have something that works well on NLP, it can help on a lot of things. So yeah, that's a quick summary of the past 2 years, I would say.
Thank you, Thomas. So next question for Nicolas. So as Thomas was already mentioning, some of the, let's say, latest developments in NLP transformers, and during your actually talk, you had a question around should or should not some of the NLP-based transformer models be used for order flow, and you actually had some kind of a, let's say, maybe semi-negative first initial approach that it's not the best way how to proceed. So if you can comment it again, because now we have Thomas here also. And the second one is like, how to still, like sometimes we can say, okay, assumptions are not met, but usually young people say, okay, assumptions, I don't care, but then they keep on innovating. So first, like, question is around what do you think transformers, NLP techniques, what can you learn for order flow that are still some kind of sequences? And then a second one is more oriented, if assumptions are not met, how to keep innovating still here?
So I mean, I think the first question is hard. I think it's difficult. I mean, I think that the point I was sort of alluding to before was that I think that the models that are used for kind of sentence-to-sentence translation, they're trying to convert one thought into another, and a lot of the and there's a lot more structure there than there is in an order book that you can look to exploit. Converting English to French or English to German, there's a lot of structure that you can look at and exploit. Word position is important and things like this. It's much harder to generalize these ideas to an order book in a way that kind of would make sense to someone who understands microstructure at a kind of deep level. And this is certainly one of the challenges that's, I think, some of the reason why it's not clear to me immediately that these models might transfer over. You can try, and we certainly should try, and we should certainly investigate. But for me, I don't think we've answered the question of what can we get from simple models first. what happens if we take the output of simple models and orthogonalize against what we know? What do we learn additionally, and what things can we discover from that kind of a research process? So I think that's sort of an answer to your first question. In terms of not caring about assumptions, well, I think that's a perfectly valid approach. I mean, you can go, you can do your work, and you can figure out what assumptions you need and what assumptions you don't, and that's really how a lot of the mathematical research proceeds. Ultimately, people say, do I need this assumption? I build some experiment, I go away and test, and then I come back with the data and I have a better answer to the question of whether I need these assumptions or not. And this is how you sort of distill models down to what the core assumptions are and what's unnecessary for a certain way. So I would be supportive of that, broadly speaking.
Thanks very much for that, Nick. I'm going to turn to Lisa Huang, who is also on Zoom here today. Unfortunately, our participants on Zoom did not have an opportunity to watch the previous talks because there's no live connection. But we had a broad range of talks, Lisa, that covered some trading and investment management related topics. But what I wanted to ask you is, what are some non-trading and non-investment management related topics in the area of finance that makes you excited?
Yeah, thank you, Peter. I was going to ask you if it's possible to watch a video of the talks. I don't know if it's recorded, but yeah, I think one of the things that doesn't get a lot of attention is how to use like AI and ML to optimize human behavior. And in doing so, that can generate or enhance what I'm calling human alpha. Most of the time, and most of the effort is in signal generation for what I'm calling signal alpha, right? But actually, a lot of the work that is being done at Fidelity, we think that humans generate alpha. Their process, their way of understanding the data, their investment philosophy, they might have honed this for decades. And this idea is actually very generalizable, not just to professional money managers, but also to retail ones. So how can AI be used to build a, what I'm calling an investment decision platform that can enhance human alpha, right? Yet, the concept of human alpha is quite elusive, right? It's like a beautiful painting that's really hard to describe. There's a connection to Polanyi's paradox. It's named after a British and Hungarian philosopher, and it's a theory that human knowledge about how the world functions and works is a lot, to a large extent beyond our explicit understanding, right? One example is that you could recognize the face of your friend in a crowd of thousands, but yet if somebody asks you to describe the face of your friend, it's really hard to do. We think AI and ML, excels at these sort of tasks, as some of the other speakers have talked about. And if you can transform some of your problems into that problem of recognition of face and using that to optimize for human behavior, I think that's a promising area. And the other area I think is that is not talked about a lot, in sort of traditional applications of AI in finance is tax optimization. Maybe because I obsess over taxes for a long time, coming from the robo-advisor background, it's really important. And in a lot of financial planning problems, multi-period optimization with respect to tax is incredibly important. And it's just free alpha, right? That's non-traditional and much easier to get with AI and then actually generating signal alpha requires a lot of data. So if you think about it, so a lot of financial problems involves tax optimization. Also, every time you rebalance a portfolio, right? If you're in a taxable portfolio, every time you rebalance, if you want to take into account taxes, then you have to do it at the lot level. Then this becomes a very path-dependent problem when you're trying to figure out tax implications at the lot level. And I think that there's applications there as well for AI ML that almost nobody is talking about.
Okay, thank you. Or we lost her.
No, she's good.
Okay. Thank you. So next question for Robert. Can you hear us?
Yep, I can hear you.
Super. Can you share maybe a little bit with us and the audience how at QB you're leveraging the latest technologies of ML and like what does it mean in practice?
How we're leveraging the latest technologies. Well, we're not using the latest technologies. We're using kind of old technologies, I have to say. So we've been looking into using GPUs, but we're not there yet. We're just running on sort of all the compute packages we have, on all the servers we have using fairly old technology. And what we've been doing actually is structuring the problem so we can optimize very quickly, which is not really latest technology, but just intelligent structuring. What I would like to talk about is what kind of problems we found are amenable to machine learning kind of approaches and which are not. So as I said before, and some people have alluded to, there's a lot of, the signal to noise ratio is terrible. So there's a lot of noise, and we all kind of have this dream that you could toss all your data into some black box and it would come out with a trading signal that would have tremendous predictive value and help you get really good execution. And that never really works out. For example, I find it's the usual rule, if you give a project to a student, if you don't know how it's going to work out already, then it probably won't work that well for the student. You kind of have to have a problem that you know you could do, and then you can help the student do it. And it's kind of the same with a computer program. So my rule of thumb that I've evolved to is if a person could do it, then a computer can do it. And just if you have a lot of examples, then it's easier to have a computer do it. So the classic example is training a neural net to tell a cat from a dog. Well, you don't expect it to do better than a person on telling a cat from a dog, but if you have 1 million of them, you need a computer. And so similarly, on things where you feel like if a person could look in detail at the data and have some idea what's going on, then maybe a computer could figure it out. But if you're asking it to do something that you have no idea how to do, it probably won't work. So that's a little bit like what Lisa was talking about, that we're trying to augment human decision-making, but we're trying to sort of capture what a human would do in certain situations and then be able to do that 100 times a second across all the products that we trade. So as I mentioned, the successes we've had have been things like cost measurement, where a person could look at 2 products and say, yep, they look pretty similar and these look pretty different. Or some decisions about how to place and when to cross, where in hindsight, they're pretty obvious. Some of the other examples that have been involved with supervising students are success stories where we build a huge complicated model with 50 different input parameters, and then as the student looks at it, it becomes clear that what's actually driving the value is just 1 or 2 factors. And so we wind up with a regression model with just 1 or 2 variables, but we didn't know that at the beginning. So I consider that a huge success for machine learning, where it lets you sift through a lot of data and come out with a simple model that you can understand. And at the end, it doesn't look like machine learning, it just looks like a regression example. So your question was about latest technology, and I guess what I'm saying is we don't really use late technology. We use very simple technology and try to get simple results, which we feel like we could do by other means if we had to, but it's just more efficient to have the computer do it. So that's what I would say about that.
Yeah, that makes a lot of sense, Rob. Thanks very much for that. I'm going to turn to you, Nick. And in your capacity as head of execution research at AllianceBernstein, maybe you can talk a little bit about your experiences of leveraging recent AI and ML techniques when it comes to optimal execution.
Yeah, sure. So, I mean, I think there's an element of what Rob is saying that's very, very true. I mean, it's very difficult to do complicated models at scale in production. This is hard, and it creates a lot of other problems that you kind of don't really want to be dealing with that to limit the success. In terms of what we are thinking about, we at AB trade a lot of products. So we trade equities, we trade futures, we trade FX, we trade options, and we trade all of these across all of the regions globally. And the challenges that we have are really to do with like automating that. You know, we trade with a lot of brokers across all of these regions, and one of the problems that we're really using ML for is to understand how to automate and be efficient in the way that we do broker selection, and really to do A/B experiments in a kind of large-scale controlled fashion. So we emulating the way that Google and co think about experiments. That's kind of what we're trying to do, because the breadth both in products and in geographies means that trying to approach this with human beings just becomes unwieldy far too quickly. So that's really what we are focused on today, thinking about how to build automated trading in this kind of multi-asset, multi-region way.
Okay, thank you. So the next question to Thomas Wolf. So how do you see a relation with respect to finance NLP in future? And you were not here, but we had one interesting also talk around the potential biases of pre-trained models and what happens with that. So two questions. So
yeah, okay, good questions. Yeah. So in terms of future, I think well, I think this is probably one of the area where it's the most interesting to try to apply NLP, right? I see two main areas where it's really, really interesting, I think. So one is healthcare, and the other one I think is finance, because so there is all these things that I think are very beautiful today, beautiful math thing about modeling relation between all the agents and how they work. But if we can tap a little bit into all this knowledge we have from text, all the things that people are actually talking about and how this has influence on their decision, we have this really huge pool of input that I think can help like solve so many factors, confounding factors, so many things that we can probably label as noise or that we can't really model clearly today. If we had this way to tackle all the information input that we have, that would be really great. So I think this is very, very interesting opportunity, I think. So obviously this rely on having good NLP model, and definitely this model are just a reflection of their training data, basically. So we need to be super careful and to know exactly what we are training them on. And bias is a big question, right? So in particular, because we tend to reuse this model. That's the point of doing transfer learning. So we all kind of start from the same model. And they definitely might be trained on some data that are quite far from what you would like to have for your thing. So for instance, I don't know, if they are trained on very American-centric data, but you actually want to model what's happening in the world in another country, you will have this huge American bias, which is okay, but that's something you need to be aware of. Even in other languages, you have some multilingual models, but they are trained. Then there you need to really understand who is the team who has been building them, right? Is this also an American team scrapping internet and filtering based on how they see the multilingual data they want for their model, which might not be the multilingual data that you want. So a good example is big science. So this is this very large training I was talking this morning, if you were there, where we try to take this approach around data, around representativeness. We try to get the data that's actually representative of what people are reading on the internet in each of these countries. So we ask people in Arabic countries, India, what are they actually looking on the internet to get some data which is representative of the world and not of our conception of the world. And that's, I think, what you would really want if you want to remodel what's happening in the world. So yeah, I think this is both a very interesting field. I think the intersection of NLP and finance, and both a tricky one, or at least you need to be very down on earth about what you're using as a model, as a data. Not use that as a black box that's supposed to work out of the box.
Thanks very much for that, Thomas. Mathieu Dixon on Zoom. I hope you can hear me. I wanted to get your take on, we've discussed trading strategies and the deployment of AI and machine learning models. I'd like to get your perspective of how to most effectively lever these types of algorithms for generating trading strategies.
Yes, I think one point I want to make, and I think it's a very broad point, but I think it really helps, and speaking more in equities, to wear two hats when you're approaching the problem of building trading strategies. On the one hand, you have this data science way of thinking, a process, and on the other hand, you really have to understand and think a little about, or a lot, about the fundamentals. And I think that the problem we run into with machine learning is what I would call the keys under the lamppost problem. And that, you know, when you're walking home late at night and you drop your keys, you know, the first thing you do is retrace your steps, and you'll probably go where the light is, you know, and try and find your keys there. The chances are you drop your keys elsewhere. And the point I'm making is I think we tend to go for commoditized data sets that are easy within reach. And the reality is that the real gains are in looking for very esoteric data sets that really exactly characterize what we're trying to do. For example, just trying to predict apples, you know, from fundamentals ratios, as opposed to, you know, looking at product strategies for, you know, new iPhone releases, and looking at competitors in that market, you know, the cost of producing, you know, better screens or more efficient batteries. In other words, you need to build up many, many models and build up a much more representative view of that particular product market. And it can't just be a sort of a broad brush, forget all of the fundamentals. So that's the first point I want to make. And I think the second point is that, and Igor Chichinski, CEO of WorldQuant, I think sets this out very well, in that you need a way to determine how sensitive your algorithm is to error, and your strategy, that is. And I think you can actually do that without machine learning. You can simulate from a distribution that you know, represents how accurate the algorithm is, and you can see how sensitive the strategy is to prediction error. And therefore, you can sort of avoid a lot of the traps of shall I improve the functional approximation error, do a lot of training and so on, and simply understand, is my strategy well suited for, you know, this type of machine learning, and what is the goal, what is the bar for the accuracy? Is it really worth me spending 3 days trying to improve the algorithm if at the end of the day the strategy is still going to fail because of latency issues, or because it's just so intolerant to you know, inaccuracies in the algorithm?
Thank you. So next question goes to Lisa on Zoom. So from your viewpoint, what are the early successes and frictions in applying AI or machine learning in investing?
Yeah, thank you for the question. I think, you know, I think one of the panelists already said it. There's definitely success in smaller timescales, right? Like in execution. The data is there, the algos have been, you know, models have been built, and the applications are ready to be deployed. In some instances have been deployed. The other item, I think, is NLP, right? I think Thomas said it well. NLP has arrived, and it's, you know, night and day even from a few years ago. So the application of NLP as a tool, a technology for investing is incredibly important. But that goes beyond what has been done already. Maybe, you know, like 5 years ago, X number of years ago, NLP is really used for featureization of unstructured data. How can you use NLP to go beyond featureization that is then fed to downstream models? Using NLP to create multimodal data sets and understanding, you know, actual topology is, I think, an interesting and important application, I think, going forward, and will probably lead to a lot of success in the future. Frictions, there's a lot of frictions. You know, it's been said already, you know, there's a small data issue, right, in finance. It's not Google style data. So the kinds of models you can apply, given that small data issue, has to be carefully curated. There's a explainability issue, right, which is that, you know, you're going to put real money here, so you have to understand how the model is functioning. There's also a talent issue, right, that it's really hard to find talent both that has domain as well as AI expertise, and it's costly. so those are some of the frictions that I'll highlight here.
Just a quick follow-up question to you, Lisa. Petter speaking here. What do you see? What do we need to do in finance to better lever the more recent NLP type of techniques? And what do you see some applications of these types of techniques from your seat?
I think like I think somebody also said it, like ML tools and techniques are kind of baseline tools now for most quants, but I think on both sides it's underestimated. So quants tend to think that AI and NL techniques are not as deep as it is, and then vice versa, right? Like if you're a deep AI expert, you think you can just pick up the quantitative domain quite easily. You can spend a lifetime on each alone. So it's really non-trivial.
Agreed. Mathieu, Rosenbaum, you gave a fantastic talk today about leveraging deep reinforcement learning to solve a very complicated problem. Reinforcement learning in finance has a lot of different challenges, especially when we're dealing with very high dimensional type of problems. Can you talk a little bit more about the challenges that you see in this area and how we may go address those problems as we go ahead?
I mean, it's true that using reinforcement learning is very tempting in finance, because when you see the success of this technique in other fields, like you really want to try to use it. The thing is that doing trials and attempts, it's usually costly in finance. So I mean, you cannot just try to see and know about your environment, except maybe you can do that at the order book level, like Rob was saying, because in that case, probably there's not too much loss or cost trying to do this experiment, and you can know much faster if it works or doesn't work. And also, if you try to use reinforcement learning directly, maybe it's not the right idea, because, well, I mean, we know about the environment in finance. I mean, it's very complex, of course, but there is a lot of structure. I mean, it was very well illustrated in your talk. I mean, so the environment is not completely random. There is structure. So if you want to use reinforcement learning, you have also to put the knowledge that you have about this environment. And according to my view, and maybe it's more my taste than my view, but I feel fascinated by the way you can solve this high-dimensional PDE with this kind of approaches. I mean, like 10 years ago, we could not imagine solve like PDE in more than dimension 3 or 4. I mean, now we can learn value function, we can learn optimal policy, I mean, for very high dimension. And most of the portfolio optimization problem can be recast in this kind of setting. So I think this is clearly a very promising direction to use reinforcement learning in finance, using that for portfolio optimization and help solve this complex HGB type equation that arise in high dimensions.
Thank you. So next question goes to Fabrizio Lillo. So there are a lot of young practitioners and students in the audience. So what would be your advice like for navigating this multidisciplinary field?
Well, that's a complicated question. Okay, in my experience, what is important is really to have knowledge on both the domain and the methods. I've seen a lot of people doing machine learning for finance, especially high frequency finance, I have to say, without having a clear understanding of how the market works, what you can do and you cannot do in the market, what are the frictions, the latency, and so on and so forth. And so this, of course, create the possibility that you find fantastic opportunity for becoming rich, but then when you try to implement in practice, this is not the case. This is perfectly fine, but I think this is one of the cases when it's very important to mix knowledge of both worlds. I mean, of the world of the methods and of the world of the system. Of course, also the same applies also on the other side. Of course, I'm not saying that this is a problem of machine learning student, but this is very important because a lot of methods cannot be simply transferred to finance, for example, exactly because there are a lot of specificity and structure that you need to know. Another very important aspect that sometimes is completely forgotten is, especially if you are at high frequency or if you are big enough, is that economic and financial system possessed with this property which is called reflexivity, or someone called reflexivity, which means essentially that when you act, you modify the system, right? While in other systems this is not the case. In natural science, this is not true. And this, of course, completely change, let's say, you should take into account about this when you take a financial decision, because otherwise what you're going to get is not optimal, because maybe in your training, or the training of your activity, you are not taking into account this one. For example, at high frequency, this is what is called market impact, is the fact that whenever you trade, you move the price, because the market sees that you are doing something. So if you don't take into account this in a proper way, then you are missing a very important aspect of the dynamics, and maybe your strategy is not profitable anymore. So, and you know, introducing a model for this is not easy, and you need to have knowledge about the system in order to be able to introduce in your forecasting model something also that tells you how the market will react whenever you trade. These are specificities that maybe are present, that are present for sure in finance and economics, but are not present elsewhere. So what I think, of course, is a layman, let's say, suggestion, of course, is of course to have a knowledge of finance, because again, of how the system works, because this can strongly undermine, let's say, the potentiality for you to become very, very rich. So.
Thank you very much. Now we know, all of us here, how to become rich. I need to write this down, so I need to take a break. Now, kidding aside here, we're going to turn into a little Q&A with the audience here as well. But one of the topics that came up here actually during the break, I ran into a friendly Swede friend of mine who asked me the question, well, you're not talking a lot about portfolio construction here in this track. So I wanted to formulate this question to the panel, and whoever wants to address this is, many of the financial decision-making problems that we have, we're making a sequence of decisions, right? We may have signals, whether these are expected return forecasts or risk forecasts. We're sticking that into some kind of construction engine to build a portfolio subject to transaction costs. And then we're also trading and building, potentially also trading trajectories as well. This is a number, traditionally this has been dealt with in a number of separate steps where we're combining these models in a workflow. Recently, there's been work done on areas, or an area that's often referred to as end-to-end modeling, where we're sticking all these different components into one coherent framework. So I wanted to see if anyone wanted to speak a little bit to your thoughts around that, and where this might go.
Thanks, Peter. So I've read some of this literature, and I think it's really, really exciting. I think the challenge with this is that a lot of the papers that I've seen, they are quite simplistic. That necessarily the input data is fairly simplistic so that the method can work. And so I think there's a gap between what practitioners would consider a reasonable input and a reasonable output, and what the methods can produce. A typical example is constraints. A lot of portfolio optimization comes with a lot of constraints. Trying to embed these in some kind of end-to-end process where a network outputs weights that satisfy these constraints is very hard. Embedding these constraints and getting some kind of feasible runtime and everything else, this is very challenging and very difficult. So in my mind, at least, I think we need better inputs, more realistic inputs, not just historical return series. No real practitioner would build a portfolio with the only input being historical returns, as well as some understanding and trying to introduce the realistic constraints, although it may make the problem significantly hard. I'm actually quite excited by this area of literature, because I think it has the opportunity to really move what is a difficult problem forward, which has sort of been stuck, really, for a number of years. We've really focused on kind of mean variance optimization for a long time, but we haven't really moved this materially forward, I don't think. And this maybe has the scope to do that.
Great, thank you very much for that. Well, we're going to take the few minutes we have left. We'll take a few questions from the audience. Who has some questions for the panel? Yeah.
Yes. So I might ask a lot of questions today. So I have a question to Thomas Wolf on the NLP. So I see among my classmates that they start putting in practice a lot of NLP in defining the risk profile of the company in order to predict the stock market of the stock price of those companies. You said something about the sparsity of the data and how long you need to train and the universalities problem. How you can see that actually it can work in this field, because as you said, it's a bit too hard to be true. What they do in a so fast time, it's working actually. There might be a bias according to the company, to the time analyzed, and also when you look far in the past, we have stock prices, but we have less news, less information, less expressivity, so less people speaking about a certain company, or we might not have the company. How you can see this actually working?
Yeah. Yeah, I think there's a couple of problem that I don't think a lot of people are tackling today in NLP, but that I think are very, very important for finance. One of them is the changing landscape of indeed like a company on knowledge. New company arise, you need to be able to model them somehow, but we are still in this paradigm of like static model, which I think will be very difficult to use in finance. So we need to move to some kind of evolving models, or at least models that are really aware of time and that you can move around so that they can, when they try to model data 10 years ago, they can actually use the relevant context at that time and not the context of today. So this is one problem, which is I think open research, and we were talking with actually just, I don't know your name, but just behind you, he was asking me about that, and I say, yeah, I don't think a lot of people are studying that in NLP today. So, but that's a very important problem to solve. And
at least there are a lot of companies on sustainable finance trying to define those type of risk profile and define how much CO2 emissions is going to be involved and
yeah.
So the question is sustainability. It's a lot of challenges when it comes to measuring various kinds of output or score companies.
Yeah.
How would we address this through NLP?
I think here that's showing also something that was discussed in the panel as well, is that you should not ask your model to do something that you don't think is possible, and typically the model will always give you an answer, and typically will take shortcuts. So I think a good field where this has been badly applied is like hiring, like screening CVs or something like that, right? You ask the model to guess based on the CV. I don't know how good somebody is here. So obviously there are some good clues that we would like the model to learn, but there are also some very bad clues that we don't really want the model to model. A good example is Amazon, that tried to replace all their screening by automatic thing, and they discovered that all the women were screened out, because in historical data that kind of happened to be the case. But you don't want the model to do that, right? You would like the model to really do what you want, and you have very easy this kind of bias that can creep in, and that will be a problem if you want to evaluate the companies. For instance, I think that, for instance, I don't know, but like the name of the company should probably not be a very important factor in the safety, or I don't know. But the model will take this kind of type of shortcuts and model, oh, if the name of the company is 3 syllables, that's a good sign. But that's the kind of thing that you don't want it to model, that kind of creep in with the bias that you have in your training data. You have more companies with 3 syllables named that are successful than 2 syllables, this kind of thing. And yeah, I mean that's a very big problem in NLP. Yeah,
we have time for 2 more questions. So I'm going to take one question here, and then we're going to pass the microphone over to you, to Unit 8 over there, right?
Thank you. I also have a question for Mr. Wolf, but it's a bit more on the technical side. I don't have a finance background at all. I'm a recent data science graduate. And I wanted to ask you, you said that you started recently working with time series data, right, at Hugging Face. Do you think that once the dedicated hardware, let's say, becomes more accessible and, let's say, evolves more and is no longer such a bottleneck, you could realistically apply BERT networks, maybe LSTMs based on BERT blocks, right? Because I know you can actually have sequence-aware models through BERT. I actually worked myself with the recommender system. And if it's possible to do that on time series data, for example, let's say to predict stock prices, right? If you could indeed, as Miss Lisa said earlier, if you heard, if you could use multimodal data and maybe have a hierarchical model and then, let's say, aggregate the representations, different representations. For example, you have a model that takes news sources about a particular company whose stock you're trying to predict and other geopolitical news or financial events into account and then model it all together.
Yeah, I mean, I'm a very outside view, so I think that's really the goal. At least I think that's something we should try to do, definitely. But yeah, I mean, maybe somebody else here has more idea about how realistic it is and what are the challenges that will come. For me, I'm really just still learning a lot about what we can do or not.
So you can find a number of papers where people are using like images of price trajectories to create alpha. You can find images of people using text, and my understanding is that most of the sophisticated hedge funds have all of the modes of data that you're describing and are combining them at the moment. The sophisticated hedge funds who have access to, of course, hardware and data and things like that. So I think this is a great idea. You may not be the first on the bus for that particular idea.
Hi, I'm Seb. I'm doing data engineering in industry outside of the financial domain. One thing that's shocked me a lot is that outside of the finance industry, most of the work is the data engineering side before it comes to the data science side. So, you know, there's been a lot of discussion today, for instance, with NLP about the data quality going in, so how it's sourced, how it's embedded before you even feed it into the model. On numerical data, I think it was briefly mentioned, perhaps we should look at more esoteric data sets than just market data. My question is, do you guys think, or does anyone think that there's a possibility on the numeric side for easy wins before we get to the data science stage and, you know, start using deep neural networks, whatever, in whether it be just simple heuristics to pre-process the data or more complex feature engineering? Could, in your opinions, is that a field that has area to grow, or is all the, you know, the easy to pick stuff being taken and now it's left up to really the hardcore modeling side to do the rest to actually, you know, get alpha out of theories in application?
Who wants to address it?
I think I have a clarifying question about that question. So is this a question essentially of ways in which machine learning can be used to essentially improve the quality of financial data sort of at the engineering stage before it goes through to the data scientist? Is that the question?
I mean, yes, but it doesn't even have to be ML techniques specifically. It could be more simple heuristics. But what I'm saying is, you know, in your opinion, is there an issue of the quality of the data that can come in? Can that be improved, or is it already at sort of the, you know, the best signals noise ratio, I guess, to throw a phrase that's been used a lot today, that we can achieve?
Yeah, so I would respond to this. So I think, you know, I've spoken to people at who run, you know, cloud-based warehouses for banks, and there's a good example of getting all these different data sets from different banking divisions, and they can see, you know, everything, and they're looking to find ways very early stage, you know, they have this data lake to be able to improve, you know, the data before it even goes any further down the pipeline. And I think, you know, things that are obvious are things like finding ways of imputing missing data. And, you know, there are issues to do with potentially, you know, enforcing properties like no arbitrage. You know, if it's, you know, if it's a volatility, for example, and a derivative price, then you've got issues, I think, to do with, you know, knowing certain properties of data variables. You know, for example, the volatility cannot be 4,000. So I think there's a lot of market knowledge that can be used, and it can possibly be used, use existing models to validate some of that data before it goes even further, you know, and sort of introduces all sorts of anomalies and things. So I think there's a lot of scope for that. I think that that's still, you know, very much the focus of, you know, tech companies who are trying to provide new platforms for big financial institutions to build ML capabilities of integrated data environments.
Thank you very much for that, Matthew. And I'm going to give my answer to that, because I've thought a lot about this problem as well. If you can clean and address the data directly before it's ingested into models, there's often a lot to be had. I think many of you have heard Huang speak extensively on this issue when you're solving small data problems, right? If you're building a classifier that classifies between cats and dogs, but some of the dogs are misclassified as cats and vice versa, well, then your classifier is going to be subpar. So you need to go through and correctly label that data. Now, that translation of manually relabeling or labeling the data, it doesn't translate directly into many of the finance applications, right? Because the example is that, you use the analogy of cats and dogs. Many of the financial problems we're dealing with, we look at a picture, and sometimes, we might say, is this a cat or this is a dog? It looks a little bit like a cat, and maybe there it looks a little bit like a dog, right? It's much more noisy. The labels that we're working with, if I'm abstracting here a little bit, are much noisier. And I don't think we have systematically explored the ways in which we should clean and finesse the data before they're stuck into models. This has been a very interesting panel, and we're coming up towards the end of this track. First, I want to thank our panelists, Fabrizio, Thomas, Mathieu, Lisa, Robert, Nick, for participating both as speakers as well as on the panel. Let's give them a round of applause. And again, I want to thank the organizers of this really great event. We hope to be back again with a little bit of luck again next year. Also want to thank our sponsors, our home institutions, NYU Courant, ETH, Big So Data, and also ISOT. You made it possible for us to invite the different speakers and bring them here in front of you guys here today. On the behalf of my co-organizers, Viva and Nino, I also want to thank our fantastic audience. You've been great. Lots of really interesting questions, both here in the room and also in between the sessions. And I hope that this conversation continues. Most of us will be sticking around here later today, and some of us also tomorrow. So please come up and say hello, and we'd love to hear what you thought about this, and we'd like to hear a little bit what you're working on if you're working on financial decision-making problems and time series problems. So with that, thank you very much for coming here today.
Thank you.